Hello, everyone. My name is Michael Keidar from George Washington University. I would like to thank organizer for inviting me to give this a talk. And I should say that my talk primarily focused on, finding a solution to help, all of us to overcome this current pandemic, and it's involved on using cold atmospheric plasma for sterilization and disinfection. And I would like to thank my colleagues, my students, postdocs, and collaborator at George Washington University, and as well as my colleagues at Drexel University. And this project is part of the RAPID grant that was supported by National Science Foundation very early in the pandemic. Something around more than a year ago, in March 2020. That's where first we actually approached NSF, and that's how it started. The object of our study is what we call cold atmospheric plasma, which is a non-equilibrium environment that contain charged particles, electrons and ions, reactive oxygen, nitrogen species, various radicals, as well as electromagnetic emission. And we started to pay in particular attention to that in the recent year or so. And these are, kind of typical spectra that you would obtain by using passive optical emission spectrometry. So you can see, various excited species, as well as some, ions of interest. We'll talk about this in a second. As I mentioned, this is non-thermal, non-equilibrium plasma. The electrons, has energy of about 310 electron volts on average, while the most of heavy species, it's a room temperature, close to room temperature. And these plasmas are generated in the air and used for biomedical application. And, your primary pathways for that use are around reactive oxygen and nitrogen species in the various combinations, and they will have various interests for number of applications, distinct applications that we will mention in a second. That also includes potentially UV emission that can lead to to viral virus damage. Radio frequency, these are some kind of recent modalities that we exploring as well. So use of cold atmospheric plasmas gave rise to the field what we call plasma medicine. And the plasma medicine is known for a number of years already, started with quite success in bacterial deactivation, but it's also used recently in the various therapies, including wound healing and cancer therapy. And cancer therapy is particular focus in my research lab. For a number of years. There are two primary devices that used in this application. One is known as a plasma jet, where the gas flow create the ionization wave that propagate outside of discharge region, as shown here, or more kind of focus discharge area, which called the electric barrier discharge, where the test object will be actually placed inside of that plasma environment, and that create kind of higher power density that may be used for some applications with a lot of benefits. So when we approach the problem of sanitation of various surfaces using the cold plasmas, there were a number of guiding principles that drove our development. And as a result, we developed number of devices, starting with this one that we call sterilization chamber. You can place a surgical mask and sterilize, and that was primarily important during the height of pandemic, where there was a extreme shortage. But there were some other devices that based on handheld device of we call plasma barrage, that can be directed to various areas of the surfaces, plasma jet that you already seen, and discharge tube, which is more of enclosed device that contain particular composition of helium and air, and lead to emission in UV range, as well as some electromagnetic emission in gigahertz frequency that might be of importance. We try to develop as simple and as cheap as possible circuit for that devices that based on waveform generator that's actually driven by machine learning algorithm for optimization, as I will show you later on in my talk, and then the power supply that also can be controlled by optimization algorithm transformer that feeds high voltage electrodes. So this device is known as a plasma barrage, and there's a link for some development of that at National Science Foundation. The variety of species that can be formed as this device interact with surrounding air, that includes, creating of, ions, excited atoms, emission in UV range, as well as some processes that leads to, destruction of the species, recombination and attachment, and as well as charge transfer and many others, in particular, if we talking about interaction with some liquid environment. So the different approaches to generate variety of reactive oxygen and nitrogen species. So these are three different discharges that we develop. One is R discharge in the open air that create primarily UV radiation. The streamer discharge in open air, which is basically known as a jet, as well as formation of streamers in the discharge tube. So these two devices primarily focus on forming reactive oxygen and nitrogen species and UV. These device primarily create UV and some limited RONs. And these two really involved a very low power consumption, and that was one of the guiding principle for our development. So in fact, we were considering a number of dilemmas for design. So on one hand, there is a need to create cheap mobile device that will be battery powered, easy to carry, easy to handle, and easy to use, of course. On the other hand, we would like to make it maybe tunable. That would, of course, includes complexity, and by tunable we mean that it could be programmable, so we can actually optimize the output. On the other hand, safety is a priority that actually involved high selectivity with respect to treating only virus and not say skin, if that might be of concern. Right. So, so as a result, there are a number of different devices that we develop. As I show, one more involves sterilization chamber, which is simple and maybe to less extent mobile, but on the other hand, discharge tube and the plasma barrage much more mobile, but more of a fixed type of conditions, less complex. And then, of course, plasma jet that involved some gas tanks, right? And I should mention that all these devices are not involved any flowing gas, but it's more utilizing air and kind of controlling discharge in the open airspace. So, what we try to optimize, of course, is to create as safe as efficient as possible device that kind of focus only on the viral treatment. And in terms of self-adaptive uh, a plasma device, it's kind of follow our guidelines of utilizing real-time feedback that can involve diagnostic of target as well as the plasma, and adjust in real time plasma parameters to optimize treatment. Of course, it introduces more complexity, but it carries quite a lot of benefits. And this is some example of machine learning, algorithm and hardware that we developed. And the goal here, of course, that to develop some, mathematical model that can guide formation or optimization of formation of reactive oxygen and nitrogen species and UV required for particular, viral density, and also looking for the lowest power consumption to achieve the same goal. And the idea here that the plasma generator can be um, used in conjunction with, say, real-time OES measurement that can be analyzed and go through the algorithm that can, predict changes in the, plasma control parameters such as discharge voltage, perhaps frequency, waveform, and the treatment period that can optimize that plasma composition. And this is more of a flow chart that shows also implementation of artificial neural network that represent those models, and each of these pathways may be channels that guided either by changes in the plasma density or frequency and perhaps gas composition. And these are some example of how this can lead to formation of optimal species. So the artificial neural network after training, after setting some particular conditions, can generate the plasma composition, and that can be in real time compared with some limited optical emission spectra. And as you can see, it's kind of very well, validated in real time. But then, changes of some of those parameters can actually use and leads to optimization of this composition for various applications. For example, if we would like, go from, say, cancer therapy to wound healing to decontamination, we are looking for some specific, peaks that may be characteristics for those applications, right? And say for cancer therapy, so hydroxyl might be one of the representative species, and that can be, maximized at least to maximal hydrogen peroxide formation. And then for, say, decontamination, perhaps ozone would be one of the product that involved, and that can lead to various typical mean electron temperature in these devices. As you can see with those applications, this temperature goes up, but that can allows you to use one device, but optimize it for various applications. This is a summary of some, past work that used cold atmospheric plasma for, virus deactivation, and you can see that there were some suggestions that this plasma treatment might be very effective. And of course, one of the important components is access to BCL3 facilities that would allow you to treat the actual SARS-CoV-2 virus. And I should say that for many researchers in this field during the pandemic, that was a bottleneck to a very large extent, because these facilities are extremely busy. They always busy, but in particular during pandemic, as you can imagine, and there are only limited number of these facilities. We're fortunate enough have one in the George Washington University, as well as in some company that we work as well. So this is a summary of recent campaign that utilize these three devices. One is a plasma jet that's shown here. The other one is a plasma box, and the radial, plasma discharge tube. And these are some results that shown that the application of low power, extremely low power, device, again, without helium flow, such as plasma box or radial plasma, for about 5 minutes, lead to about 1 log reduction. Right? So just going a little bit in the details. So these are some procedures for virus preparation. The SARS-CoV-2 specimen isolated from the clinical patient and at George Washington University, and then was growing. The virus was collected between 48 and 120 hours, and then harvested virus was placed in vials, and that used in the lab as shown here. And this is kind of typical setup. We used 6-well cell plates with about 10 to the 5, 10 to the 6 now cells in the plate, and we growing at kind of typical conditions. And then we used plasma is a plasma box, or this arc plasma with with multiple mirror for treatment, or plasma brush that I showed before. And in addition to helium guided plasma jet, right? So there were 4 different devices that used in the studies. So these are some preparation techniques. So the treatment up to 5 minutes, the positive control where the helium only was used, and of course negative control is serum-free media. And then the sample was collected, and this shows that viral spike on the coupon. Then it was dried, or it was remained in a wet condition, and then was treated by the plasma. Then we elute the virus in serum-free media as a negative control, and then we kind of count number of kind of viral live cells with the virus, and then we read the plug, say, after about 3 days. So these are some kind of typical condition, and the goal here, of course, is to find plasma condition that allow 2-3 log reductions, right, under either wet virus test or dry virus test. And these are some typical results for virus on the surgical mask surfaces. So we see that we are getting something a little bit more than a half logarithm reduction under those low low power condition in both wet and dry virus test. So overall conclusion from that first campaign was that the destruction of SARS-CoV-2 is possible with a cold plasma, and using under 2 kilowatt device would require about 5 minutes, and that can lead to about one log reduction, which might not be sufficient. And as a result, we went ahead and with the same procedure started to apply high voltage of about 10 kilovolts that lead to very same result after just about 10 seconds as opposed to 5 minutes. So this really significantly depend on the power. But of course, you have to optimize power. Looking into some other guiding principles such as simplicity and low power consumption and such. And of course, going to extreme at very higher power of about 16 kilovolts in argon lead to very, very strong reduction of 2 to 3 logs, and the virus and the different surfaces, as you can see here, the plastics and metal and football surface and such. There's a paper that published recently by my former student. And in addition to the surface treatment, of course, we were looking into airborne virus treatment. And these are works that done primarily our collaborator under the same grant at Drexel University. And the idea here was to create tubular dielectric barrier discharge that would allow airflow passing through and treating the virus on the droplets. And this system was characterized, unfortunately, only in BSL-2 to the moment. So they were able to characterize that on E. coli as well as MS2, but in both it shows very strong effects of over 3 log reduction after about 5 minutes treatment as shown here. But again, this is BSL-2, and we are planning to do in BSL-3 experiments shortly. And this is summary. I outlined several cold plasma systems that were designed and directly tested on SARS-CoV-2. Machine learning was used to help to optimize the chemistry of the device that was guiding principle, for us to really improve, design and reduce complexity, and also make it as simple as a user friendly as it possible. Treatment time required is about 5 minutes if a low power used, or close to 10 to 30 seconds if medium 10 kilovolt voltage used. High power jet characterized by about 16 kilovolt applied voltage, reduced by 3 logs at about several minutes. So I would like to acknowledge support from National Science Foundation, and of course, a lot of work was done also in collaboration with FDA and the local company BioQuel that actually continue these experiments as we speak now on our newest devices. So, and also I would think, all colleagues, students and postdocs in my lab, and these are, lab members, of course, before COVID and during the COVID. And I would like to thank you and happy to take any questions. Thank you.